Swayam Prabha. Digital India. Educated India.
Welcome to Module 52 of Point-Set-Topology course Part 1. So, today we shall take up the study of normality again. Characterization of normality. Characterization in terms of continuous functions. In fact, we will have two different characterizations which are closely related to one another. One is due to horizon, and then using that, another one is due to T-say. The central idea is that the set of all continuous real-valued functions on a space must be able to reveal some properties of the space itself. Often in algebraic geometry and sometimes in algebraic topology also, this is the central theme. Look at the set of real valued or complex valued functions, or those which have some extra properties and so on, declare them as what is known as coordinate space, coordinate ring. And then the ring will dictate all the geometry and topology. So this is the theme they follow. We don't go into that depth here, but the idea of why we need such a thing like characterizations, only for that reason I am telling you. So where it is much more important than to us. So we can ask a vague question: how large is the set of all continuous real-valued functions on a given space X? The study of this leads to a different kind of topological results altogether, with applications to problems such as, I have just mentioned a few of them here: metrization problem, embedding problem. Embedding problem is just means that take a space, whether it can be embedded inside some Euclidean space of finite or infinite dimension, and exploring the interrelationship between the ring structure, the algebraic structure of CXR, with the topological properties of X. So these are the few things. For example, when you go to function theory, it is not all continuous functions they take. They will take analytic functions. Okay, so that is what is important for them in complex analysis, for example. If you go to algebraic geometry, they will only take polynomial functions. Okay, so it depends upon. For us, if you want to study the entire topology, you must better take continuous functions. Okay, in differential topology, you will take differentiable functions, smooth functions, and so on. So we shall not be able to discuss any of these topics. I mentioned 3 of them in this course, more than what I mentioned. And I have mentioned it only because why the Uri-Jones characterization or T's characterization is important. But some of these problems and applications will be taken up in part 2 of this course. Okay. So let us proceed with these characterizations. How one might have uh, come up with this kind of thing, I would like to tell. I cannot read Euryzone's mind, nor I can go back in history and so on. Okay, in being go back in time. So I'm guessing that this may be the one which led him to consider such a thing. So again, go back to metric spaces. Take any subset A, consider the distance function from A. So distance function is defined from X. Okay. D underscore AX is equal to DXA. You can write in two different notations, which is nothing but infimum of all the distance between D comma X comma A, where A ranges over A. X is fixed. So that is the distance from A. Okay, the infimum of all these systems. For the point X, distance between X and A is defined like this. Okay, it's easily checked that dA is continuous. Okay, on the whole of X. And clearly, if A is inside A, then D of, we can put X equal to A, so that will be 0. So infimum will be 0. So it will vanish, right? But it will vanish on A bar also. In fact, A bar is precisely the set wherein this function will be identically 0. Okay, so that is easy to check. Huh? Now let B be another set. Consider the function g from x to r defined by gx equal to dxa minus dxb. For A and B, we have defined dxa and dxb. Take the difference. I have no speciality here. First I took A, and then I am taking B. That is why I am rightly. Otherwise, I could have taken dxb minus dxa also, as good as this one. This function is again continuous because it is sum of two continuous functions, difference of two continuous functions. And it is non-positive on the closure of A because the first term will be 0. And on the closure of B, it is non-negative because the second term will be 0. Okay. Now you take a special case when A and B are disjoint closed sets. When A and B are disjoint closed sets, at least one of them must be non-zero for all the points because A and B are disjoint. So if dxa and dxb are both 0, x will be inside A intersection B. So there is no intersection, right? That's it. Therefore, the sum function will never vanish. dxa plus dxb. What does that mean? I can divide by that function. Okay. Sum and difference are both continuous. Sum is never 0. Therefore, this quotient function is also continuous. I am calling it as f. Okay. So fx is the difference function divided by the sum function. Why one should think of this one is itself a moot question. But I think I have thought about this one, so Uri-Jones must have thought about this one. How I thought about it, also this mystery. I could come up to this one after long thinking. Oh, this must be the reason. Then f from minus x to minus 1 plus 1 because the numerator, modulus of the numerator is never bigger than the modulus of the denominator. Okay, denominator is already non-negative, actually positive. So this is always the value will be between -1 and +1. Okay. Moreover, A and B are closed subsets. We know that f of A, x belongs to A, this is 0, this is 0. So it's minus of D divided by plus D, which is -1. Similarly, f of B equal to +1. So you see what we have produced is a continuous function from the whole of x, which vanishes exactly, which is exactly -1 on A and +1 on B. Okay. Now you can take just a small neighborhood of -1 and a small neighborhood of +1. I have taken sufficiently large, namely -1 to 0, and here 0 to 1. Only thing is I have been careful that they are disjoint open subsets in -1 to +1. Take the inverse image, call them as U and V. They will be disjoint open subsets. Okay. Clearly, they contain A and B respectively. Okay. So suddenly, what we have proved is that disjoint closed subsets of metric space can be separated by open subsets. Actually, they can be separated by continuous functions. So in particular, every metric space X is normal. Indeed, since every metric space is normal, a subspace of metric space is also metric space. It follows that every metric space is completely normal. Okay? It's completely normal. Also, we have seen that singleton sets are closed in a metric space. That means they are Frechet spaces. Therefore, complete normality implies regularity as well as Hausdorffness also. Okay. Once they are Frechet, regular implies Hausdorff. Complete normality implies regularity. Complete normality implies normality. Okay, anyway. So all these things are true for a metric space. So why I am guessing is that perhaps this function f was the motivating example for the celebrated result known as Urysohn's lemma. Of course, it is due to Urysohn. There is no mistake in that. So this is the lemma. A topological space X is normal if and only if it satisfies the following Urysohn's condition, you see. So again and again, I will be requiring this condition. So I have named it as UC, Urysohn's condition. What is this? For every pair of non-empty disjoint closed sets A, B in X, there exists a continuous function f from x to 0, 1 such that fa is 0 and fb is 1. See, if fa is singleton 0 just means that A has to be non-empty. Similarly, B has to be non-empty. For that reason, we have to assume that they are non-empty disjoint closed sets. Okay. Otherwise, in the statement of Urysohn's, definition of Urysohn's normality, you should take whatever definition you take, 3 of them. Even if A or B is empty, it's okay. It's not so, it doesn't cause any problem there. But if you want to have function theoretic characterization here, then you have to take A and B are non-empty. A and B are non-empty. Then only you can write Fa is 0 and Fb is 1. You can also do -1 to +1 here by changing the interval, the codomain interval by homeomorphism. Okay, so that is not so crucial. Getting a closed interval as a codomain, okay, and getting a function f from this one, wherein the two sets are going to two distinct points. That is the crux of the whole matter. It could be Fa equal to some A and Fb equal to some B, where A and B are distinct points of this. Okay, so that's a crucial matter here. All right. Okay, so one way is obvious, which we have seen already in some sense. Assume that UC is satisfied by X. Take A and B, any two non-empty disjoint closed sets, okay, and take a function f from x to 0, 1, continuous function, so f is 0 and fb is 1. Then take 0 to half open, and half to 1, again half open. Take the inverse image, call them as u and v. They will contain A and B respectively. So that is the condition for Urysohn's the normality. If one of them is empty, you can always take, suppose A is empty, then you can take U empty and B equal to all of X. So that is obviously satisfied. There is no need to worry about that. So normality is satisfied if UC is satisfied. The converse is where we have to work hard out. Well, hard work is done by Urysohn. We are doing hard work in a different sense. We have to learn them properly, right? Okay. Now let X be normal and A and B be non-empty disjoint subsets. The second condition, the definition tells you if you take A and B complement, A is contained in the B complement, A is closed, B is open, there will be a open subset G such that A is contained inside G, contained inside G bar, contained inside B complement. So I am using the second condition in the definition of normality. So we have started a process here. There is going to be a iteration of this. So I am denoting the first iteration by this G by G half. Okay, this notation will be clear in a moment, so you have to wait. Right now it would be better if you write it as G1. Okay, so but now what I want to do, that's what I have to tell you, apply the normality to both the situations. So this is almost like, this is one point and there is another point, and I have chosen the half of the middle of them. If you have chosen middle, from the first point to middle and the middle point to the second point, again you can choose middle of them. So that is the kind of thing that is going on here. But middle doesn't make sense. Something in between with the relation of what? Inclusion maps of sets. That is what is being done. So what I want to do is now between A and G half and G bar half and B complement. Okay, I introduce two more open subsets which we shall denote by G1/4 and G3/4 respectively, such that from A to G half is open, A is closed. G1/4 will sit there, contained inside G1/4 closure. Similarly, G half to, okay, we have come up to G half, right? G half is contained in the G half bar. That's already there. We are using that one now. This G bar is G half bar. G half bar to B complement, twice again open. We'll have one more open subset there, G 3/4 contained inside G 3/4 bar. See what I have done from 1 by 2. 1 by 2, half of that is 1 by 4. Between 1 by 2 and 1, I have 3/4. So keep on cutting down by half. What are those numbers? Next time you'll get 1 by 8, 2 by 8, 3 by 8, 4 by 8, 5 by 8, 6 by 8, 7 by 8, right? So those are numbers. So what are they called? They are called dyadic rational numbers. Rational numbers whose denominator is always a power of 2. But I want only all of them between 0 and 1. I am including 0 and 1. 0 is taking the place of A, okay, and 1 is taken, the B complement is taking the place of 1 there. I don't need to write any symbols for them. In between, I'm going to put all these open sets such that they are contained inside their own closure, and then the closure is contained inside the next one, and so on. So that is what I'm going to do. Next step will be an open subset between A and G half in G 1/4, and one on this side also, in everywhere in between. G4 is open, G4 is closed, and BC is open. So between them, I can put one more open set and so on. So go on squeezing open subsets in between. Okay, so let D denote the set of all dyadic rationals in the interval 0, 1. Namely, integer divided 2 power n, m and n are positive integers. Okay, m less than 2 power n, you can take m to be only odd numbers if you like. If there is some power, you can cancel out. But I want m to be less than 2 power n already. Okay, carrying on with this process, we obtain to each number here an open subset GT. Okay, so all these new open subsets of X are indexed by this set. So what is the property? All of them are neighborhoods of A. A is contained inside GT. GT is contained inside GT bar. GT bar is always contained inside B complement. So this much is obvious. But more than that, between T and GT and GS, what is the relation? As soon as T is smaller than S, okay, GT bar will be contained inside GS. So this is the property. Okay, for example, it does not depend upon whether I have chosen them first or second or third and so on. It depends upon whether the corresponding indices are bigger or smaller. For example, the first one that I have chosen is G half. In the second stage, I chose G 3/4. So G half bar is contained in the G 3/4. Okay. So next I will be choosing 5 by 8 or 7 by 8 and so on. So you have to compare the numbers first. That can be compared. The corresponding sets also must be compared in a stronger way. Namely, the closure of the smaller indexed one must be contained inside the other open set. So GT bar is contained inside GS. Okay. All that we have done is repetition of the normality condition inductively. Okay. Now we have produced a continuous function out of nowhere. The crux of the matter is the dyadic rationals are dense inside R. Okay. So once you have some way of nominating these indices, one can cook up functions out of that. That is the whole idea. So define fx equal to 1, okay, if all the x is all in gt complement for all t. It does not belong to any of gt's. Okay. See, all GTs are inside what? GT bar itself inside B. Okay. So B complement. So if they are not in this itself, X is inside GT complement, then I am defining it as 1. Okay. Otherwise, I will define it as infimum of all t such that X is inside GT. See, at least this set is non-empty. Therefore, infimum makes sense. Okay. Anyway, this set, once it's infimum, once it is non-empty, it is bounded below. All these numbers are bigger than or equal to 1, actually bigger than 1, 0. So it's bounded below by 0. So infimum is a finite number. If it's empty, then you would have a problem. So whenever it's empty, you just define it as 1. That is all right. Take the infimum of all x such that all t such that x is inside gt. Okay. Since all the gt, all t's are between 0 and 1, infimum, whatever this set is, it has to be between 0 and 1. And this part is 1. So 0 is less than equal to fx less than equal to 1. This is obvious from this definition. Now, the first one says what? All the GTs contain A, closures are contained inside B complement. So from this it follows that f of A will be 0. The infimum of all the dyadics inside 0, 1 is 0. And f of B is 1 because it is x is not in any of them, then only it is 1. So if it's in B, it cannot be in any of GT. So it's in the complement of GT for all of them. So the set theoretic property is already done very easily. The missing point, the important point is that f is continuous. Okay. Producing continuous functions, very few such results are there. Even proving, after proving something, we have to prove homeomorphism, so on. They are easier. Here, producing continuous function itself. So this is something fantastic that Arizona has done. So first we observe that the collection of all intervals of the form 0, a and b open 1 for 0 less than a, b less than 1 forms a subbase for the usual topology on the closed interval 0, 1. The usual topology, and then I am taking restriction. So I have to restrict the subbase also. So I don't want to take anything other than intervals which are subintervals of 0, 1. You have to take open there, but this is a closed interval. So 0 closed, A open, this will be also an open subset. That is the difference. Similarly, B open and 1 closed, these are also open subsets of the closed interval 0, 1. If you take B plus, say, suppose you take minus epsilon to A and intersect it with 0, 1, what do you get? You will get 0 to A only, right? So this is what it is. Hence, once this is a base, subbase, it is enough to prove that to continuity of, I want to prove continuity of this. F inverse of 0A is open. Similarly, F inverse of B1 is also open, where A and B are arbitrary points of 0 and 1 open. For that, I am explicitly proving that f inverse of 0 is union of all the GTs such that t is less than a. Okay? Each GT, remember, is an open subset, so union is also open. For all 0 less than a less than 1, I am going to prove this. Similarly, f inverse of B1, I am going to prove its union of all GT bar complement. You see, bar is closed, complement is open. Again, this is an open subset, but now this time T is strictly bigger than B. Okay? So 3 and 4, if I prove, the theorem will be complete. All right, let us prove 3. Take a point x inside x such that it is on the left-hand side. What is the meaning of that? F of that x is strictly less than a. Of course, it's always bigger than or equal to 0. Okay. This implies, remember what is the definition of fx? Infimum of all t such that x is inside gt. This is fx is less than a. Okay. What is the meaning of infimum is less than some number? There must be something here which is less than that. So there existed gt such that x is in gt and this t is less than a because infimum is taken over all such t. So I have not done anything other than just definition of infimum. Okay, not very serious also. Infimum is also. So LHS of 3 is contained inside RHS. For each point x, I have found a GT here. All right. The other way inclusion is obvious. As soon as x belongs to GT, infimum will be smaller than that. Okay, and t is less than a, so it will be here. F of fx will be less than a. Right? Even if one t is such that x is in GT and that t is less than a, it will be infimum will be smaller than a. So it is f of x will be less than a, so it is here. So this way containment is obvious. All right. So fourth one, to prove 4, so let us take x, which is that b is less than fx less than 1, less than or equal to 1. If fx is 1, then remember when it is 1, it is inside gt complement for all t contained in belong to d. No gt will contain it. It's in the gt complement. So fix some s belonging to d such that s is bigger than b. Take some s inside d because b is less than 1. Between b and 1, there must be some s. What is s? S is an element of d. So this is where I am using the fact that the dyadic rationals are dense. So we can find a t belonging to d such that this s is less than t. See, I have chosen b less than s less than 1. So between s and t, I can choose s and 1, I can choose another t. So that is also again density of this result. So I can choose actually b less than s less than t and t less than or equal to 1. It follows that gs bar is contained inside gt. This was the choice property 2, right? And hence x is inside gs bar complement. Okay, x is in gt complement. Okay, its gt complement will be contained inside gs bar complement. Now consider the case, one case is over, namely if fx is 1, x belongs to one of them. Remember what I have to show. I have to show that the point in the left hand side, namely point which looks like this one, b less than fx less than or equal to 1, is in the union of all gt bar, and so I have found one such gs bar complement. Now it may happen that b is less than fx and fx is strictly less than 1. When fx is strictly less than 1, it is a second condition, namely fx is infimum of all t such that x is inside gt. This means that there is a t such that, okay, x is inside gt, first of all, right? And then you have to take that fx is bigger than b but less than 1 is what I have done. Also, it follows that x is not in gs for any b less than s less than fx. If that is the case, then fx would be infimum, it will be smaller than that one. So if s is smaller than fx, x cannot be in gs because fx is the infimum. Okay? So now you take b less than r less than s less than fx. Again, I am using density of d here. Okay. Then x cannot be in gs implies that x cannot be in gr closure because all the closure of corresponding things are contained in the gs. Okay, which is same thing as saying that x is in gr bar complement. So we have found out another element which contains on the left. Hence, LHS is contained inside RHS. So you see, the proof of 4 required us to use the density of D at least 3 times here. So proof of 3 was easier. The proof of 4 took some time, right? We have not yet completed the proof. What we have to do? RHS is contained inside LHS, right? Even that is also not, in the third case, it was very easy. In this part, little more, you have to say. Suppose x belongs to RHS. RHS is what? Union of all G bar SC, namely G bar complements. So x is in one of them for some s which is bigger than b. That is the definition of the right hand side. This implies that x cannot be in GT for all s bigger than t, that's bigger than b. So between between s and b, if you take another t here, x will not be inside GT because x is not in GS bar itself. X is inside GS bar complement. Okay. On the other hand, suppose x is not in the LHS of 4. Okay. I took it is in RHS. I want to show that it is in the LHS. LHS means what? B is bigger than fx. Fx is of course bigger than equal to 1. So that is the meaning of x, right? So if that is not the case, that's what I am telling you. Hence, so suppose on the other hand, x is not in LHS, then fx must be less than or equal to b. Fx is less than or equal to b means what? Infimum is less than or equal to b. Okay, then x must be in GT for some for all t bigger than b, because the infimum is less than or equal to b. Right? If something is bigger than b, x must be x is already inside some GT. Bigger than that one, it will be definitely inside that, because GT is contained inside GS for all t less than s. So, but that is absurd because we have just shown here that, just here we have shown that x is not in GT as soon as t is bigger between s and b. But here it says that for all t bigger than that, it should happen. So that is absurd. So LHS will be RHS will be contained inside LHS. You start with a point in RHS, it contains a LHS. This is what it is. So this proves for, and hence continuity of F is established. Therefore, the completion of the proof is done. Okay? So I made some remarks here. In UC, I have already done this one. I will repeat it. We can freely use any closed interval AB, A less than B, in place of 0, 1 by merely composing within the linear homeomorphism T going to B minus A times T plus A. Often it is convenient to use the interval minus 1 plus 1 instead of 0, 1. Like the metric that we considered, d of xa minus d of xb divided by d of xa plus d of xb, it was between minus 1 plus 1. So that is what we are going to do next time. But sometimes you may have to choose some other numbers also. So any closed interval you can take, no problem. Okay, that is the comment here. There is no assertion about the uniqueness of the continuous maps. In the UC, there exists some function, continuous function. There may be plenty of them. In that, there are lots and lots of functions. The difficulty was showing that there exists one. After that, you can cook up many, many of them. Okay. So, one of the special function, very specific one I want to have, and I am going to use that. So I am going to introduce a notation here. Okay. Temporary notation, like in measure theory, you have the characteristic function. Let us introduce a temporary notation which we will use in the proof of next theorem that we are coming. Given any two disjoint closed subset A and B of X, let us denote chi of AB. So it depends upon both A and B. A function, a continuous function from X to minus 1 plus 1, such that on A it is minus 1 and on B it is plus 1. There are many of them. Okay. Any of them I will just call it as chi of AB. Depends upon the context. All that I need is it has this property and it's defined on the whole of X and it is continuous. That is why I am just writing this chi of AB. The only thing that we need here is that if X is normal, then such functions exist. Such continuous functions exist. Okay. So choose any one of them and temporarily write it as chi of AB. So this is what I'm going to do next time. I'm going to use it next time. So this comment also I have made, but I will repeat it. We have mentioned that normality is not hereditary. We have not proved it. However, it is weakly hereditary. Namely, every closed subspace of a normal space is normal. That's very easy to find out, easy to prove, because closed subspace of a closed subspace is closed. So start with Y as a closed subspace of X. If A and B are closed subspace of Y, then they will be closed in X itself. Therefore, normality of X will produce open subsets in X which contain A and B and disjoint. Now you intersect it with Y. Okay, so Y will be normal. So closed subspace of a normal space is normal. Okay, and that information is important and we are going to use that also in the next theorem. Okay. So let's stop here for the next theorem tomorrow. Thank you.